So in this video we're going to look at graphing polar equations, and we're going to do it without using a table of values, and we're going to do it by thinking about the equation, and then if we need to, by trying to convert it into rectangular form to see if rectangular form helps us graph the polar equation. So here I have the equation r equals 4, and this is one, if you think about it, you can come up with the graph of this without having to do any conversion over into rectangular coordinate system. So this is one where thinking about it carefully should do the trick. So radius equals 4. The radius is constant. So you just need to think, what geometric object has a constant radius? Well, a circle has a constant radius. So here I have the radius is always 4. So that would be the locus of points. That was always a distance of 4 from the pole or the origin. So that's just going to be a circle of radius 4. So if I think about graphing it, whether I'm in a polar coordinate system or rectangular coordinate system, you would just make a circle whose radius was 4. And we could use the relationships that we established in video 1. So the Pythagorean theorem says, hey, x squared plus y squared equals r squared. So we get x squared plus y squared equals 4 squared. But the Pythagorean theorem in this context is the equation of a circle. So there's the equation of a circle whose radius is 4. So here I have theta equals negative pi over 4. This is a little more subtle, but it can also be done without converting into a rectangular coordinate system. So what you would think about is, if I'm in a rectangular coordinate system imposed over top of a polar coordinate system, so we just impose them one on top of the other, theta equals negative pi over 4. So remember, in polar coordinates, theta is the angle that we make with the radial axis, and the radial axis always corresponds to the positive x-axis if we've imposed the two coordinate systems on top of each other. So this is saying I need an object that always makes an angle of negative pi over 4 with the positive x-axis. So that's just going to be the line through the origin. It's going to be the line through the origin that makes an angle of negative pi over 4 with the positive x-axis. We could use the tangent of theta equals y over x to convert it into rectangular coordinate system to verify that result. So we could say the tangent, if we know the tangent of theta equals y over x, well, then if theta is negative pi over 4, then the tangent of negative pi over 4 needs to equal y over x. But what is the tangent of negative pi over 4? Well, if you think about where you are located on the unit circle, if you're at an angle of negative pi over 4, then the xy coordinates associated with that angle are x equals 1, y equals negative 1. So the tangent of negative pi over 4 is just going to equal negative 1 over 1, which is negative 1. So the tangent of negative pi over 4, you replace it with the y coordinate over the x coordinate, but negative 1 divided by 1 is just negative 1. And then if you multiply both sides by x, you're going to get the opposite of x equals y. So we have the rectangular equation y equals negative x, which is just a line whose y-intercept is the origin, which is what we have here, and that has a slope of negative 1. And if you have a slope of negative 1, you are making an angle of negative pi over 4 with the positive x-axis. Here's one where I think it's hard to come up with this equation without converting it into rectangular coordinates. This says the radius is always equal to the opposite of the cosecant of theta. And the issue is theta can be many different values. So here we have a variable controlling the radius. So this one would be hard to think about. So converting into converting into rectangular coordinates is going to be a useful way to visualize the equation in this context. So here's my xy coordinate system imposed on top of my polar coordinate system. I want to look at this and say, hey, I have the radius equals the opposite of the cosecant of theta, and the cosecant is just the reciprocal of the sine, right? Cosecant equals 1 over the sine. So if you multiply the cosecant times the sine, you're going to get 1. If you multiply something by its reciprocal, you get a 1. So something that we could do here is multiply both sides by the sine function. Multiply by the sine, multiply this side by the sine. So on the left-hand side, we get r times the sine of theta, and over here I have negative. The cosecant times the sine, because they're reciprocals, is going to equal 1, and I get r sine theta equals negative 1. But then I want to recognize from my trigonometric relationships that y is r times the sine of theta. So this can be replaced with y equals negative 1, and so that's going to be the line through y equal to, this is y equals negative 1 through negative, the line through negative 1. So there's some examples of graphing polar equations either by thinking about what it has to be, or by converting it into rectangular coordinates where maybe we're more comfortable thinking about what things look like. We're more practiced with it.